For centuries, classical physics modeled light as a smooth, unbroken electromagnetic wave, sweeping continuously through space and distributing energy evenly. But when researchers began shining high-frequency light onto metal surfaces to study the photoelectric effect, the metal ejected electrons in a way the continuous wave model couldn't explain. The mathematics simply broke down. To solve the crisis, Albert Einstein proposed that light doesn't interact with matter as a continuous wash of energy. Instead, it hits in discrete fragments. He argued that radiation is built of individual, quantifiable packets of energy. Today, we call this particle the photon. To accurately map how light interacts with the microscopic world, we have to put aside the classical wave and look at the rigid rules governing these individual light particles. The first rule of the photon model is that a single particle's energy is completely dictated by its frequency, which our eyes perceive as its color. This schematic shows a photon's mathematical blueprint. Its energy, E, equals its frequency multiplied by Planck's constant, h. Though lacking mass, a photon carries momentum, also locked to its frequency. Every photon of a specific frequency always carries the exact same energy and momentum. No matter the frequency or energy, all photons share one universal trait. They travel through a vacuum at the exact same velocity, the speed of light. A photon is a highly standardized packet of physics. Once you measure its frequency, you have its entire mathematical profile. Because of our experience with flashlights and lasers, it is easy to assume that a brighter beam contains physically larger or more powerful photons. In this split-screen diagram, the left side shows a low-intensity beam, a sparse stream of individual photons. On the right, high intensity simply means more photons crossing every second. Notice the individual photons are identical in size and energy to those on the left. Cranking up the brightness dials up the volume of particles, but it does nothing to alter the baseline equation of the individual photons inside the beam. The energy of a single photon is strictly independent of the overall beam's intensity. Brightness is a measure of quantity, not particle strength. This distinction is exactly why a dim blue light can knock an electron out of a metal plate, while a blindingly bright red light cannot. We know how these particles are measured, but how do they physically navigate through a universe filled with external forces? The third rule is that despite being born of electromagnetism, the photon itself carries no electrical charge. It is entirely neutral. Because they are neutral, photons cannot be bent, slowed down, or pushed off course by ambient electric or magnetic fields. They pass straight through. But the definitive proof of the particle model happens in the exact microsecond a photon collides with solid matter. Watch this slow-motion schematic of a photon hitting an electron. The force transfers instantaneously, like two billiard balls colliding. It obeys strict physical laws. The total energy and momentum the photon brought perfectly equals the ejected electrons. The balance scale is flawless. There is just one unique exception in this subatomic crash. While the total energy is conserved, the photon itself is completely absorbed by the electron. The energy lives on, but the individual particle is destroyed. Because light strikes matter with an exact, measurable momentum and obeys rigid conservation laws upon impact, it operates as a solid, quantifiable entity. It is a particle.